All right, hello. Hi, this is Dr. Matsko, and this is our first video lecture of the semester of actual recording. I apologize, my handwriting is really bad, but you guys already knew that, so hopefully you'll be able to read what I'm writing, and hopefully you'll be able to hear what I'm saying. If there's any problems with this lecture, with understanding what's going on, then please email me and reach out. I myself will listen to this again afterwards, even though I don't like hearing my own voice, but we're going to try. All right, so today I'm going to cover diffraction. The goal is I'll talk a little bit about the formulas, but that's covered in your textbook, and I'll go through some problems. That's also covered in your textbook, but this is just to reinforce all of this. And actually, I'm not going to embed any questions in this video. It's just up to you. You can watch as you would like, whenever you'd like. This is just extra help for you in preparing for the exam and also in doing the homework. All right, so let's jump in. Diffraction. All right, so this is a review of Huygens Principle. As I mentioned in class, this principle, Huygens Principle, will help you understand the foundation of what's going on with diffraction, with single slit diffraction, as well as the double slit interference. It's very strange to think about. I'm not going to actually test you on it, but as the more times I mention it, the more likely it is that you will wrap your head around what's going on. The math of it, again, is very beautiful, and when you do your PhD in physics later on, you will definitely have to derive this math. Maybe when you get there. All right. So Huygens Principle states that if you have if you have a line of lights, if you have a plane wave, right? This is just if I'm showing just the crest like that. And so this is just the crest, and it's moving forward. Oh, you can tell that some of it's thicker. Okay, sorry. Some of it's moving forward. Instead of just thinking, oh, it's moving forward in a straight line like this, which would be the straightforward way of thinking, if you were a mathematician, you would say, okay, any line can instead be broken up into a whole lot of dots, right? And that's also the idea of like calculus, right? Any line can be a whole bunch of dots, and these dots are emitting lights in circles. And so you can basically integrate all of these circles and add together what's going on, and then you could figure out where there's a tangent line to all of those circles, and that's going to be your next crest, right? So you have one crest, and then you have the next crest is by figuring out the tangent line. And of course, it should be a straight line, unlike what I'm drawing. It should match what you would expect otherwise. But anyways, this is cool math. That's the whole point of it. It's just a bunch of dots move, and they become these dots, more dots further on. You can draw them as a line, but those dots, I got to figure out how to change colors here. There we go. Right? And that also becomes dots, and those become circles, right? Circles. And then you have your next line, and then those also become dots, or you imagine them as dots, and those have circles, and so on and so on. That's your next line, and so on and so on and so on. All right, so this is Huygens Principle. All right, so what does it have to do with anything here? Well, I showed you, I talked a little bit about this has to do with refractive index. The subject of today's lecture is diffraction. If I can figure out how to change slides. This one? Whoa. How come my slide is not going anywhere? What did that do? Oh, that's black? Okay. Oh, seriously, why am I not getting the slides to go anywhere? Whoa, okay. Technical difficulties. Keep. Okay, let's just open the next slide and see if we can get this to work properly. Okay, hi. Okay, well, this is the next slide. Here we go. All right, so diffraction. First, we're going to focus on the simplest, which is single slit diffraction. And now I changed. Here we go. Let me change colors. Right, so here in single slit diffraction, right, earlier. Okay, there. Right, so last chapter we did double slit. This is a single slit. So we're imagining that we have some kind of wall or something, some piece of paper or whatever, and there's one hole in it, right? So that's going to be our single slit. Single slit. The one hole in the wall, right? Let's see, an aperture. We'll find out. I forget if this is on this is not on another slide. Okay. So we call it a single slit, but actually the math is totally the same if actually it's an obstacle. So you can do this for single slit. And in that case, you have the slit has a width of A. We're using the letter A. You can also use this for a single obstacle. Obstacle. And that's for, again, if the obstacle has a width A. So actually the exact same math can be used for either a single slit or a single obstacle. I'm going to explain it using a single slit because that's definitely more intuitive to understand. Thinking about obstacles is another step up, but the math is all the same. The equations are all the same, so we will leave it there. All right, so for a single slit, let's see. When incident waves encounter an edge, obstacle, or aperture, the size of which is comparable to the wavelength of the waves, right? So that means A has to be about the same order of magnitude as the waves, right? So light is on the order of hundreds of nanometers of a half micron, and so that means A has to be approximately 1 micron. Right now, space. 1 micron is we're talking about things that are very small. It could be up to hundreds of microns, and you'll still get some of this behavior, as we'll see in the next problem. Our first problem I'm going to cover. All right. But so we have our single slit, and again we have, let's see, what color are these? These are basically red, right? And so we have this red light coming in, right? And as it goes through the hole, we're going to break it up into a whole lot of dots, just like Huygens Principle. Here, this image from the textbook actually is just breaking it into 4 dots, just to keep it simplified. But you can also imagine it's a lot of dots. But it's a lot of dots, and then once we've broken it into dots, we can picture it as like the double slit or like a multiple slit. Right, we have, and then we can look at this interference, and I decided not to derive for the double slit, and I'm not going to derive the single slit either. Anyways, we're going to have an interference, and we have a path length difference. Sorry, you can't even cover that. Path length difference is going to be A sine theta, just like we got for the double slit was D sine theta. This is going to be A sine theta. Okay. Blah, 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 blah. Okay, so we have some interference. Okay, let's see if I can actually change page. There we go. All right, so we have our A sine theta, which is, I forget, the path length difference. Path length difference, it's what the textbook likes to call it, difference. But anyways, A sine theta, and that has to equal some m lambda, or n, the mode is some integer. So this is the same idea as we got for the double slit. There's some kind of integer. You're going to have 1 is the central. And then you have 2, 3, 4, 5, etc. Bar, and it goes on and on. Okay. These graphs to the side are showing, let's see, they've all set, it's telling you this one's a equals lambda, this one's a equals 5 lambda, this one's a equals 10 lambda. Let's see, and then you have theta on the bottom, theta, and then you have relative intensity. All right, so actually I'm going to look at the bottom one first, right? You're going to have this peak right at the center, but then you see there's these two minimas right there on either side, and it's totally symmetric. Let's see, and they're separated by minima. Oh yeah, that's another very important thing of this equation. This is for minima or dark spots, right? And so these first minima are the m equals 1 spots, and you can see there's second minima going on, that's m equals 2, and then you can kind of see close to the edge of the graph m equals 3. Right, so that's for the bottom, right? For our middle graph, I think we can see just the m equals 1 and m equals 2. And then for the top graph, fine, m equals 1 is maybe over here. Right, but we don't see it on this graph because it's so far away, because a equals lambda, right? So it depends on lambda, right? So the wider the slit is, or it depends on a really. And so the wider the slit is, the larger a is, then the narrower the maximum, right? So that's why this one on the bottom, a is large. And so the minima are close together, or you could say like the central peak is very narrow, but up on top, a is small. And so the that central peak is very large. All right, a is small, right? And eventually, if you get if a is 1 dot, then you get basically what you would expect, which is that it's just all spread out. Right, so let's see. All right, so I think I have problem on the next one. Yes, okay, turn slide. Oh, there we go. All right, let's do a problem. A human hair is placed directly in front of the opening of a laser pointer. Well, anyway, so a human hair, and so that counts as our obstacle. So you have some light coming in. I don't know, this detail about being in front of a laser pointer is not important. Let me change color. Oh. Let's see if I can go back. There we go. And there we go. Okay, let me put my human hair right there. Okay, now again, the math of this is all the same, but it's just kind of strange, right? That if you have your light coming in, and then you can look at the different angles, right? That's our theta, right? And you want to know what's going on in the screen over here, right? You're going to have a huge central maximum here, right? Maybe I can draw this sideways. You think I could draw it? Let's see. All right, I'm going to have to draw it like this. You're going to have, I'll try to draw it sideways. All right, you're going to have a huge peak here, all right, and it's going to go down, and then it's going to bounce and bounce, and it's going to bounce and bounce and bounce like that, etc. All right, so this is what our intensity is going to look like on the screen or on the wall, whatever's over there. All right, so you have a human hair, a single obstacle that's in blue, is placed directly in front of the opening of a laser pointer, whatever, that's our laser. The light has a wavelength, lambda, of 532 nanometers. On a screen 2 meters in front of the laser, or in front of the human hair, a diffraction pattern is observed with the central minima spaced 0.0164 meters apart. Determine the approximate thickness of the hair. All right, let me see if I can get different color going on here. All right, so we're told the screen is 2 meters away. Let's see. So here's our human hair. I'm going to call this the screen. And so this is, no, I'll call it L. We haven't really done anything with this yet. And this is not part of the equation, right? All right, so this length here is 2.0 meters. Let's see. The diffraction pattern is observed with the central minima. These things are 0.0164 meters apart. 0.0164. Right. Determine the approximate thickness of the hair. That thickness is A. So find A. The central minima is m equals 1. We're given lambda up here. Oh, can't read that. Lambda's up there. And we want to find A. And so what we need to know is theta. So as you might be expecting or imagining, this geometry is basically giving us theta. Let's draw this over here. Right, basically I have a right triangle here, theta, and so this is 2.0 meters, and I'm told that this whole length here is a 0.0164, but theta is only what's going on in this top triangle. So I have to find out what this length is, and that's going to be 0.0164 divided by 2. Right, we know it's exactly half because there's the symmetry going on. Right, so I got to plug that into my calculator. I have not yet figured out how to do a fancy calculator like Khan Academy. So instead, I have my laptop here. Okay, and I'm getting that this equals 0.0082. Wow, okay. So I have a triangle, theta, 2.0, 0.0082, and then we have to figure out what is this, sine or cosine or tangent, right? All right, so we're going to have tan of theta equals opposite over adjacent, so 0.0082 over 2.0, and so theta equals arctan of 0.0082 over 2.0, and I'm going to plug that into my calculator. Arctan of 0.0082 divided by 2.0 in degrees. I misspelled degrees. There you go. 0.235 degrees. Wow. 0.235 degrees. All right, so we got theta, and I gotta make some space here. Do I have an eraser? Oh, I do have an eraser. Okay, I can erase some of this over here. Okay, let's go back to continue in black. All right, so we have our equation. A sine theta equals m lambda, and we can plug in. We're looking for A. Okay, we have sine of 0.235 degrees equals 1, right? We said m equals 1 because it's the central minima, and lambda is 5 532 times 10 to the minus 9 nanometers. And so that means A is going to be 532 times 10 to the minus 9 divided by sine of 0.235 degrees. All right, let's plug that into the calculator. Crazy stuff. All right, 532 times 10 to the minus 9. I put an 8 minus 9 divided by sine of 0.235 degrees. And I got, okay, 0.0001, I'll put 30 meters, which equals what? 130 microns, right? 130 microns, which is actually around what you'd expect for a hair. Hair is around 100 microns, 50 microns, 250 microns or so, around there. So, oh, go back. There we go. So there's our answer. That took me a long time, but mostly because I'm teaching this, right? You guys would be doing this much faster, right? You would just have to find theta over here, and then you would plug that into there, that equation. So once you get used to this problem, it's actually very fast and straightforward to do. All right, so let's see, moving on. Here we have, this is a multiple choice question. Again, I'm not going to make this into a Canvas question or anything. It's for you to think about. I encourage you to take a second and try to figure out this on your own, right? I'll read out loud. In a single slit experiment, what effect on the central maximum of the diffraction pattern would result as the wavelength of light is decreased? So as lambda is decreased, right, and then the central maxima again is basically that, right? What's going on? It specifies the width of the central maximum, right? So there, width of central max. I think maybe after a couple of weeks of these lectures, I'll get used to writing on iPad. All right, so what happens to the width of the central max? Right? All right. Should I sing the Jeopardy song? Okay, anyways. All right, so I hope you thought about it. Hope you chose one. All right, so let's see. Okay, so wavelength of light is decreased. Let's see. So over here, our lambda is decreased. Let's see. We're focused on the central maxima, and so m stays as 1, right? Let's see. A is constant. A is not going to change, right? But if your right side is decreasing, that means your left side also has to decrease. And so that means your A sine theta decreases. All right, so what does that mean for sine theta to decrease, right? For sine theta to decrease, well, I don't know why that's decrease, then theta also decreases, right? For sine theta to decrease, then that means theta decreases. For theta is between 0 and 90 degrees. All right, so we know theta is going to be between 0 and 90 degrees. And so that's why theta must decrease. Right? So you can think of, if I get another picture over here, not a color, I mean, right? So that means that theta is going to decrease something like that. Oh, it's still going to have the same peak, but instead it's going to be whatever. It's going to come closer. No, why my pen's doing that? right? So the width of the central maxima is also decreasing, right? Is decreasing, right? Right. If lambda decreases, then sine theta must decrease, then theta must decrease, and so the width must decrease. All right, so our answer here is going to be B. All right. So I want to, that's double slit diffraction. I want to build on that a little bit. First, I'm going to talk about diffraction by double slit. Sorry, what am I saying? That was single slit diffraction, right? Single slit diffraction. All right, I'm going to build on that with a double slit. So that means we're going to have a double slit. So you're getting interference by the double slit, but you're getting diffraction by each individual slit. Okay, so this is the next step up. Let's see. So here in A, it is labeled, right? Okay. These are, so here at the top, this is what we would normally see by double slit. Right? That's what we talked about last lecture. Here on B is what we see with single slit. Right? Right, we have these. Right, so with double slit, we have lots of up and down and up and down and up and down. Right, with single slit, we have a broad central maximum, and then we have minima. Right, let's see, with double slit, we had what, d sine theta equals m lambda. Right, and that's for the peaks, the maximum. Right, and for a single slit, we have a sine theta equals m lambda, and that's for the dark spots, the minima. And if we combine them, so both are in effect, the interference and the diffraction are in effect, then we get, again, these bright spots related to d sine theta, and we get minima related to a sine theta. And so you can see it's almost like an envelope, right? You can, that's what we commonly call it, the envelope, that the outer intensity fits what's going on with the single slit, right? But all of these inner things fit the double slit. Sorry, I'm getting like I'm having trouble with my words here, but there you go. Single slit versus double slit. All right, so here, let me do practice, right? I know the textbook goes into a lot deeper if you want to spend more time with it, but let's jump into some practice. We already have red going on in here. I'll switch back to orange. Oops. All right. Oop. Okay, a beam of monochromatic light with a wavelength of 660 nanometers, that's ugly lambda, is directed at a double slit with a distance between the slits D and a slit width A. So that's a hint. It's giving you both values. That means both are in effect. The graph of the intensity on the resultant screen is shown below. Consider the points labeled in the drawing, including the central maxima, which is labeled A. Center. Okay. Which one of these fringes is produced when d sine theta equals 660 nanometers? And which one of the fringes is produced when a sine theta equals 660 nanometers? All right, so we got a sine theta equals m lambda. 660 nanometers, that equals 1 times lambda, right? Because lambda equals 660. Right? Lambda equals 660. And so, now let's start with part A. part A. D sine theta equals m lambda. And we know that it's 660 equals 660. So m equals 1. Right? And so this is basically, can you differentiate between these two ideas? So d sine theta, where m equals 1, that means it's the first bright spot. Right? For double slits, if m equals 1, then that means it's the first bright spot. And so for double slit, here at A, that's actually m equals 0. And then the next one over, B, is m equals 1, And so the answer here is B. Fringe B is where d sine theta equals m lambda, 660, right? And so for the second part of the question, which one of these fringes produce when a sine theta equals m lambda equals 660? So again, that's m equals 1, right? And so this A, right, that's for our single slit. And so we know for the single slit, when m equals 1, that's the central minima, or the first minima, right? And so we can draw our little envelope, and it goes down, and it comes up, and it goes down, and it comes up, right? And the first minima, our central minima, is going to be over here, and I just covered the letter, okay. And that's going to be our m equals 1 for the single slit, and so we got E over there. So the answer for this is E. Okay. This is where I say, do you guys have any questions? But this is a recording, so I can't ask for questions. So please email me, or I might put up a discussion or something. Anyways, please ask if you have questions. All right, next problem. Okay. All right, what happens to the locations of the maxima for double slit interference when the size of the slits is reduced? All right, so this is asking specifically for double slit interference. So it's telling us to focus just on this d sine theta stuff, okay? So we're going to ignore that for now. Ignore the single slit for now. Okay, for double slit interference, what happens to the maxima for double slit interference? So we're focusing on the d sine theta equations when the size of the slits is reduced. Size of the slits is A. All right, so what happens to these left equations when A changes? There is no A in either of these equations, right? And so it doesn't matter. Okay, what happens? Nothing. Oh, sorry, I was supposed to give you a chance to answer this. Okay, whatever. Okay, reducing the size of slits has no effect. Okay, so the answer is A, nothing. Right, let me make sure. Distances increase, no, not that one. Distances decrease, no, not that one. It increases the number of maxima, no, not that one. Reducing the slit side only decreases the number of maxima, no, not that one. Okay, yeah, answer here is A. All right, now next step I want to bring up. Oh, this is really pretty. I love diffraction gratings. All right, so we were talking about diffraction by a single slit, right? That's what a few slides ago we were talking about diffraction by a single slit, and then we were talking about diffraction by two slits. But what happens if you have a lot of slits? Like this image has 1, 2, 3, 4, 5. What happens if you have 5 slits? Okay, and this is, or even more than that. So this is called the diffraction grating. Diffraction grating is what happens when you have a series of slits. Let me see. I'm going to give an equation. The next slide will be an equation. A series of slits, such as like greater than 5. So anyways, you have a lot of slits and it separates an incident wave into its component wavelengths. And this is an application of it. Application. You can do other stuff with it too. But anyways, it's what happens when you have a whole lot of slits, and then you look at theta. Okay, and I got a Google Photos thing. Okay, go away. Go away. Okay. Theta. And so what you find is that actually it does depend on wavelength, just like all the other things we've been talking about. It depends on wavelength, which is why for blue, you're going to get one position. For red, you're going to get a different position. But also, I think basically I should update this slide. But one of the key aspects of this is that you get a maximum. The max are very narrow, and that's another key advantage to what's going on with diffraction gratings. You get very, very narrow, and then slits, and then lots of wide minima. So that's another thing that this is commonly used for. All right, so let's get into equations. All right, so diffraction gratings, blah, 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 same thing. Diffraction by n slits, right? So for this picture on the right, I have n equals 5, right? N is the number of slits. The positions of the maxima are actually the exact same as double slit. Same as double slit. It's exact same as double slit. D sine theta equals m lambda. But the half width, kind of like how big these spots are. Here's the different pictures that I got, right? This here has to do with the width. And typically we talk about something called half width instead of width, but whatever. Actually, I'm not going to have you use this equation. Okay, optional equation, but I think it's interesting to think about. You should at least understand conceptually that the half width depends on n. There's an n down there, right? Right, so the width of the lines decrease as n increases. Okay? As n increases, this delta theta decreases, right? So the more n's you have, then the narrower these spots get. And then also you can see here there's red and there's green. And maybe you can see that the red is a little bit further than the green. Anyways, but that depends on what lambda. All right. Another cool, interesting application of this is DNA. Actually, so this diffraction gratings is commonly used for X-rays and for crystallography, for a variety of things. And actually, the textbook talks about it more in detail. There are specific fields where this is used all the time, but I'm not going to go into such detail. I will mention, just as an interesting ethics point of view, is that actually this woman, Rosalind Franklin, she was the one who figured out how to use diffraction gratings, or actually she figured out that DNA is a diffraction grating. DNA is a diffraction grating. And actually other people had been doing this too, or other people at the same time were doing the work. But Rosalind Franklin was the one who actually got this picture, and this is the definitive picture, definitive proof. So she was able to take the picture. She did the experiments. And then it was actually Watson and Crick who were able to determine, based on the picture, right? So this was Franklin. And then based on the picture, we have Watson and Crick analyzed it. And they found out that DNA is this double helix. And actually, I don't know who this Wilkins guy is. I gotta be honest, I don't know. I forgot. He was some coworker or something, I forget. But anyways, Watson and Crick analyzed Franklin's picture, and then they published a paper basically on their analysis, but they didn't give the credit to Franklin, even though it was Franklin's picture, which is totally bogus. And then that went on for a while, like, oh, you should have given credit for her. And at one time they were thinking like, oh, maybe we should give credit to her. But actually soon afterwards, Rosalind Franklin actually died of cancer. Unfortunately, at a very young age. I forget what it was, what the age was. But then afterwards, the scientific community went on to think that this was such a groundbreaking work, it deserved a Nobel Prize. And so they gave this work a Nobel Prize in 1962. Their policy is that they will not give the Nobel Prize to someone who has already died. You have to be living in order to get the Nobel Prize. But Rosalind Franklin had already died, already passed away. And so they decided to just give the Nobel Prize to Watson and Crick and Wilkins, who were still alive. And so, no Nobel. All right, which is Nobel. Sorry, misspelled Nobel. Which has gone on to be a controversy to this day. I mean, should they have not given the Nobel Prize at all then? Because Franklin was a key component of it. Right, so she deserved the Nobel Prize as much as Watson and Crick. But even before she passed away, Watson and Crick still did not give her the credit that she deserved. And the Nobel Prize is basically just evidence of how they treated her. And so did they choose to exclude her because she was a woman? Maybe that's what most people say. Or maybe they were just playing preferences and they were buddies, and so they give each other credit and they just ignored someone who was not their buddy. I don't know, but either way, this really goes to show that science can be very unfair at times. Unfortunately, science is done by real people, and real people have issues. Real people are sinners, and this is just one of many proofs of it, but is one of the more famous proofs. So, all right, with that discussion, let's go on to some little bit of a couple of more problems. I think we're almost done with this lecture. All right, so let's just finalize it with a couple of problems. All right, so let's see, what do we got? Okay, visible light with a wavelength of 589 nanometers is incident on the diffraction grating that has 3,500 lines per centimeter. Actually, if you buy diffraction gratings, they're usually going to be described by this, lines per centimeter. I can hear my son playing. Anyway, so lines per centimeter, and then at what angle theta with respect to central maxima is the third order m equals 3 maxima observed. All right, so we have our equation d sine theta m lambda. We're looking for theta. M is 3, lambda is 589 times 10 to the minus 9, and d, we're going to get d from this 3,500 lines per centimeter. D is distance between lines. All right, so what does this mean? Distance between the lines. Oh, and so actually all that we end up doing is D equals basically the inverse of 3,500, but we ends up being in centimeters, right? Because we have basically centimeters per line, right? So distance between the lines equals distance per line. So, but that's in centimeters. Okay, so I need to convert it to meters, and that's the frustrating thing. Okay, well, D equals 1 over 3,500 ugly, centimeters. I need to convert that to meters. So that's 1 over 3,500 and 1 over 100 meters, right? Because there's 100 centimeters in a meter. Right, so it should be getting smaller. Yeah, divided by 100. Okay, great. So, what is that? We just combine the zeros here. We can just multiply the denominators by each other. And 1 over 350,000. All right. And so that's what we got for D. And so what do we got? 1 over 350,000 times sine of theta, and theta is what we're looking for, times 3 times 589 times 10 minus 9. So theta will equal arc sine of 3 times 589 times 10 to the minus 9 times 350,000, right? Because you end up multiplying that. Okay, so I gotta plug all of this into my calculator. Arc sine of 3 times 589 times 10 to the minus 9 times 350,000 equals 38 degrees. Theta equals 38 degrees. All right, so there you go. There's our answer. All right, and it's less than 90, which is good. It should be somewhere between 0 and 90 degrees, so that's a good way to double check. All right, so here's a multiple choice question. I will read it out loud and give you guys a second to pause and answer it. Let's see. 2 monochromatic beams of light, one red and one blue, are directed at the same spot on a diffraction grating. The resultant diffraction pattern is observed on a screen located a short distance behind the grating. Which of the following best describes the observed pattern? All right, that equation's there just for reminders. All right, okay. Now I'll give you guys a second to think about it and choose an answer. I need to find some music for this. Maybe you could pause. Sorry, I'm a soprano. Okay. Let's see. So it breaks it in. These answers break it into central max, and then what happens to the maximum on either side. Right? We know that the center, right, the central maximum is theta equals 0, and for theta equals 0, actually lambda does not matter, right? It's going to have a peak at theta equals 0 no matter what, and so we're going to get purple, right? Because red plus blue equals purple. There are certain things like this I'm hoping that you learned in kindergarten, I don't know. And so we've already narrowed it to A and B. Let's see. The middle is going to have both colors, going to be purple. The other things that I'm hoping that you have reviewed or have learned, I've told you before somewhere, that you should know that lambda of red and lambda of blue, you should at least know which one's longer. I'm not going to expect you to memorize the numbers for them, but at least know which one's longer. And actually lambda for red is longer than lambda for blue, okay? We should know that, right? So if lambda for red is longer than lambda for blue, then that means the thetas should be larger. So that means the narrow one will be blue and the outer one will be red. And actually I have a picture of that here, right? So in our middle, we have purple, right? And then the, let's See, going that way is theta, right? So the first one is blue, and then we have red, right? That's our m equals 1, and then we have m equals 2, and etc., etc. So your blue is always going to be closer to the center, and red will be further apart. And you might actually get to a point where they're going to lap each other, I guess. You could call it that, right? But yeah, if you have a whole lot of n, if n is large, then these peaks will be narrow enough that you'll actually be able to see them between each other, right? If n is too small, then your red and your blue will overlap, and then you'll get purple, all right? But that's also one of the reasons why these diffraction gratings, they usually have n in the thousands, if not millions. Actually, they're usually very large. All right, so that's our another nice application or interesting application of this diffraction grating. And that brings us to the end of lecture today. So the point of this lecture, we covered what diffraction was. We talked about single slit diffraction. We talked about double slit diffraction, where you have both A and D, and you get a superposition. You have both in effect. And we also talked about diffraction gratings, and the half width, you know conceptually. All right, I'm not going to make you actually calculate this, but know conceptually. That is, n gets larger, that theta hw, or whatever, the width of the central maximum gets smaller. So that's it for today. I hope you enjoyed the lecture. I will put a place on Canvas for you to ask questions, and I'll try my best to be on top of it. We can continue communicating even through online. We will make the best of our situation. So praying for all of you to stay healthy and safe, and I'll see you again in the next lecture.